Horizons are the visual line at the farthest distance one can see from an unobstructed location on a curved surface. The distance to the horizon can be calculated, and that information can be used to determine if one can see something on the planet's surface from a certain height. Horizon calculations vary per elevation above sea level, but since most people are relatively close to sea level compared to the radius of the Earth, a constant of 6,350 kilometers can be used to represent this radius. This is multiplied by the height above the surrounding surface, so elevation relative to the surrounding elevation can be determined. This is to determine a number that is doubled and square rooted. That number equals the approximate distance that one can see to the horizon. However, there are more factors that determine distance one can see. One of them is refraction. Refraction on the Earth is very important in determining the distance you can see around the horizon. The horizon distance can be increased visually that you can see because of refraction. The curvature of the Earth prevents you from seeing very far. A point up here, trying to see around the curve, cannot see something that is right here, but because of refraction, light bends around the curve of the Earth to the point that the person is standing, so that they can see even farther.
That's right.
So essentially, refraction is the warping of light in a different medium other than air. When we're talking about water, for example, with this straw, you can see that light makes it look like the straw is bent. Now, if we were to project this onto a real-world situation, if you were looking out into the farthest distance that you could see, the pressure of the air molecules would actually change how you were viewing the horizon. So it would actually increase your distance by about 300 meters or so. It's not a large distance, as you can tell with here. It's not that big of a break, but it does actually affect the way you're seeing it. And that's what you should know about refraction.
Okay, so for our project, we are theoretically going to be on top of the Carolina Grande Hotel in South Carolina, Myrtle Beach. All right. We're going to assume that it's about 220 feet tall because we have 21 stories and a story is about 10 feet. And we're going to imagine that we're on the top of it. And I'm 6 feet tall, so we're going to be using 226 feet as our value for height, and we're going to see how far the horizon would be from 226 feet, or 0.07 kilometers. All right, let's have some fun.
Hey guys, our calculation can only go as far as your eyes can see. All the way back there, you probably can't really tell, but it's the farthest part in the back of the background. That's what our calculations are measuring. Now this right here is more for fun. We're trying to see if theoretically we could view Bojangles from this far away, imagining that there was no debris, like no trees or anything, and we could see Bojangles. Probably gonna be true, but we're gonna do our calculations anyway.
Yay! Yeah! Bow time! Hey!
In order to calculate the distance we could see at the horizon from the place we were at earlier, we used the approximated distance formula. We took the radius of the Earth, which is 6,350 kilometers, multiplied by 6 feet, or 0.0018 kilometers, times 2, and we took the square root of that to give us an approximated distance of 4.78 kilometers, is what being the distance that we could see on the horizon from that point.
Now, the distance from where we were to Bojangles was approximately 0.96 kilometers because we used Google Maps and looked at it. So theoretically we would be able to see it if there weren't a lot of trees and stuff, but obviously there were things inhibiting our view.
So now, it's bow time.
Alright, I'm gonna do something really weird.
Terrestrial refraction.
Misconception. Look cannon. Misconception. I'll leave your brain stimulated.
Slang came from a land where they suffer from the effects of depravity like gangbanging and earthquakes. Most famous no-namers.
I don't know where the mouse went.
Terrestrial refraction.